Hello science fans, it's the final physics video for physics paper 1 and this is all about the particle model of matter. First thing we want to talk about is that there are three states of matter. I'm sure you know this, but they are solid, liquid and gas. I've made some notes here that solid is the most dense state and gas is the least dense state. We'll come back to density in a few minutes. It's important you know that solids and liquids are incompressible. That means that you can't squash them. They are the size that they are. Gas, on the other hand, can be compressed and can be squeezed into a much smaller space. And that's because the particles in gas are spread far apart, whereas the particles in solid and liquid are already squashed right up next to each other. Talking of particles, let's have a look at that. So matter, or stuff, is made of small lumps called particles. Please don't use the word lumps in your exam, please use the word particles. As we said, we've got solid, liquid and gas, and it's important that you can describe each of those three states of matter using the correct words in the particle model. So here we go. First of all, solid. You can see from the diagram that the particles are in a regular arrangement. That means that they're lined up neatly, a bit like sort of soldiers, shoulder to shoulder. So they are in a regular arrangement. Secondly, they are closely packed together. There's no room between them. And thirdly, they all vibrate about a fixed position. So they vibrate left to right, up and down, side to side. The hotter they are, the more they vibrate. But they stay in position. So they vibrate about a fixed position. Next, let's look at liquid. As you can see from my terrible drawing, particles in liquid are not in a regular arrangement, so we say they are in an irregular arrangement. That means that they're not lined up all beautifully and neatly. They are still packed close together, but not as close as in a solid, so we describe them as loosely packed, but they are all still touching. And they can move around each other, so they don't have to stay in a fixed position. And that's why a liquid can flow, whereas a solid doesn't flow. Finally, gas. Well, as you can see from the diagram, the particles in a gas are spread right out inside their container. There's no order to them, so we call that an irregular arrangement, just like we do with a liquid. But we notice now that they are spread far apart rather than being packed together. And finally, their movement, well, they move in random directions at various speeds. So you need to describe solids, liquids and gases using the words that we've just gone through. Okay, number 3. I mentioned it a few moments ago, density. Density is quite a straightforward thing. We use the letter P in equations for density, and you can calculate density by dividing the mass of an object by the volume that it takes up. So density is mass divided by volume. Volume is just the space that it takes up. So in letters, that would be P for density equals M for mass divided by V for volume. Solids have more particles in the same space than liquids or gases, so they are more dense. Underneath there you can see the triangle for that equation. So we've got mass at the top, density, the letter P, that means density, and volume over on the right hand side. Okay, number 4, gas pressure. Why do I feel a joke coming on? You need to know a little bit about gas pressure. So here we've got a drawing of a glass jar with a gas inside. You can see the little particles of gas, and that's a lid on there, so it's a sealed unit. But you could equally think about a balloon or a football. The pressure inside that vessel being the jar, balloon or football, is caused by the gas particles colliding with the inside walls. So the particles collide and bounce off the inside walls. Don't forget there are billions of particles and many millions of collisions per second, and those collisions form the pressure. If you increase the temperature of that gas, then those particles increase their kinetic energy. That means they move around faster. If they move around faster, there are more collisions, and they are with greater force. So the pressure increases. If you increase temperature, you increase pressure because there are more collisions with greater force. Right, we're doing well here. Let's look at number 5. Number 5 and 6 are related, and they're to do with changing state For example, moving from solid to liquid or liquid to gas. Don't forget the things I'm about to talk about work equally well if something's going from a solid to a liquid, i.e. melting, or going from a liquid back to a solid, i.e. freezing. So firstly, you need to know about specific latent heat. Don't get this confused with specific heat capacity. That's a different thing and in a different video. Specific latent heat means the energy needed to change the state of 1 kilogram of a substance but without increasing its temperature. What that means is if you've got a 1 kilogram block of ice at 0 degrees centigrade, it will happily sit there as ice unless you give it some extra energy. That extra energy is used to break the bonds between the ice particles and allow them to flow like water. That energy will not increase the temperature of the ice, it will just break the bonds. So that's what the specific latent heat is, the amount of energy needed to change the state of 1 kilogram of a substance, break the bonds so it can go from solid to liquid or liquid to gas, but without increasing the temperature. Don't forget, the same amount of energy is released if something goes back from being a liquid into being a solid. There's an equation for this. Energy, the amount of energy required, is the mass of the substance, times by the specific latent heat. In an exam, you'd be given enough of these things to be able to work out whatever it is they're asking you to work out, and that equation is not one that you're expected to remember. Energy equals mass times specific latent heat. E equals m times L. I've done a little diagram there, just showing we've got two particles, and the bonds between the particles are what's keeping it as a solid. If you can break those bonds or loosen those bonds, it becomes a liquid, and if you can break them completely, it becomes a gas. There's the triangle for our E equals m times L, energy equals mass times specific latent heat. There's our triangle. There are two versions of specific latent heat because it works for melting. The equation works for melting, and that's called the latent heat of fusion, and it works for boiling, which is called the latent heat of vaporization. Every different substance has got its own values for both of those things. You're not expected to know any of those. The final thing is a heating curve, and this is a graph that shows what happens when a substance is heated or cooled. We're showing one for heating, but if it started at the top and worked its way down, it will be for cooling, but it tells the same story. First of all, let's look at the axes of the graph. Firstly, up the side is temperature in degrees centigrade. Along the bottom, it usually says energy supplied, or it could say time. In order to make sense of this graph, I'd like you to think of a metal pan sat on a gas stove, and inside the metal pan is a block of ice. The lid is on the pan, and we've lit the gas stove, and we're going to leave the gas stove lit without adjusting the amount of gas. That's going to stay as a constant. To start with, the energy that's being transferred from the burning gas is being transferred into the ice, and it's being used to heat the ice up to the melting point of ice. This is true for any substance. It could be a lump of iron that's being heated up until it melts. The point is, until it gets to that melting point, which is 0 for ice, 0 degrees, the kinetic energy of the particles, that's the amount they're moving, is increasing, which means the temperature is increasing, but the potential energy, which is the energy locked up in the bonds between the ice particles, is not changing. So my little diagram here shows that when you're below the melting point, as you increase the amount of energy being transferred, as in we've left the gas stove running, the ice is taking in energy, and that energy is heating the ice up until it gets to 0 degrees. So its kinetic energy is increasing. The potential energy is not changing because that's to do with the bonds, and we're not doing anything with the bonds until we get to the melting point. Once we meet the melting point, then things change a bit, and you'll notice the graph goes flat because the temperature stops increasing for a while. But we haven't turned the gas off, it's just the energy that's being transferred from burning the gas is now being used to break the bonds, or certainly loosen the bonds between the solid ice particles. That allows the ice to melt. During this phase, The temperature of the ice doesn't increase, so the kinetic energy does not change, but the potential energy does. Once you've got all of the ice melted, the liquid water starts to heat up again. And so the kinetic energy increases as the temperature increases. So that's the amount that the water particles are moving. But the bonds aren't affected during this phase, so the potential energy doesn't change at all until you reach the boiling point, when once again you hit a flat spot, and now the temperature doesn't increase whilst energy is diverted to breaking the bonds in the liquid so it can become a gas. That means that the potential energy increases, but the kinetic energy doesn't increase because the temperature is not changing. You can see that every particle has got what we call internal energy, and that is a combination of the kinetic energy, which is how much each particle is moving, and we measure that using its temperature, and the potential energy, which is the energy related to the bonds. So every particle has internal energy of those two types, and on our graph below, the internal energy is constantly increasing, but sometimes it's the kinetic energy as the temperature rises, and sometimes it's the potential energy as the substance changes state. Okay, that's particle model of matter for paper 1.